Hi everyone, Assalamualaikum warahmatullahi wabarakatuh. So we are from Group 7 and today we are excited to present our project which is the event management system. So I'm the team leaders for this group. My name is Nur Ijra Hafizah binti Abdul Aziz.
My name is Nur Laila Shahada binti Muhammad Azhar.
My name is Nur Shazana Husna binti Muhammad Shafi'i.
And my name is Nur Umira binti Johari.
Let's go take a look our overview. So first we have a description and then how the application works, present the algorithm and present the existing application code, and lastly is our conclusion and summary. So I will pass to Umira to tell you guys about the description for the event management system.
Okay, so the description is the event management system simplifies organizing, scheduling, and managing events. It leverages the FVL3 data structure for efficient storage and retrieval of the event details, ensuring balance and data access. The system supports operations such as creating events, updating event details, deleting events, and searching for events based on specific criteria. The FVL3 ensures quick and efficient operations, maintaining performance for each operation.
How the application works. So,
the application operation for add event is insert a new event into the FVL3. Events are stored in a sorted manner based on their unique key. And then for search event, finds an event based on its key, such as ID or name. The FVL3 allows for fast retrieval due to its balanced structure. For update event, it modifies the details of an existing event without disrupting the balance of the FVL3. For the delete event, remove an event from the FVL3 after deletion. The tree rebalance itself to maintain efficiency. For display events, users in order traversal to display events in sorted order, making it easy to view upcoming or past events.
Okay, next is data organization. Okay, our system use the FVS tree to store the event. Think of the tree of hierarchy of the box. So we have tree, which is key, value, and height. So first is the key, a unique identifier. So this is a label of each box, like the event ID. It's unique. You can quickly find exactly what you're looking for. And then for the value, event details such as name, location, and description. So inside the box are the event details, its name, location, and all the stuff. And then for height, this is like a tag that tell us how deep a box is in the hierarchy. So it helps us to keep the tree balance. This method ensure that every event has a designated spot and we can access it super fast. Next is storage pattern. Now you might wonder why do we need a tree at all? The FVL3 storage pattern is what makes it so powerful. So first is efficiency. So for whether you are editing, deleting, or searching for an event, it happened quickly. So wasting time scrolling through endless data. And then second, for balancing structures, after every operation, the tree adjusts itself to stay balanced, ensuring it does not slow down as more events are added. And then for third is sorted data, and the events are arranged in order like a timeline. So the first one is, let's say we start with the tree event ID, which is 10, 20, and 30. Here how the FVL tree will arrange them. Everything is perfectly balanced. Each side of the tree has an equal number of a label. Next, we would like to editing a new event. So now we add an event with 15. The tree will temporarily look like this. So the left side is now taller than the right side. This imbalance could slow things down if it not fits. So next, we will do a rebalance for the tree. Here where the FVL tree is shine, it automatically rebalance itself for rotating some nodes. After the adjustment, the tree look like this. Now the tree is balanced again and we back to lightning fast operation. I will pass to Shazana to present the algorithm.
Okay, so thank you, Israel, for the previous slides. This one is present the algorithm. Okay, so the operation chosen is the add event. So this algorithm is to add a new event to the system by providing the event name, date, and location. So this is the algorithm. Okay. So the question is to find the running time and estimate the efficiency of the algorithm. So first, for each of the two add event, the method performs, we have three key operations. First is object creation, which has time complexity of big O of 1. And then we have the adding the event to the list, which typically big O1 unless the resizing is required. And then they will, number 3, will printing a confirmation message, which depends on the length of the message. But it is considered big O1 for short strings. And then the second step is the list starts with a assuming by a capacity of 4. And then when we attempt to add a fifth element, the list will resized. So the current element are copied to a new array which double the capacity, which takes big O, C, which is the current capacity. And then after resizing, the new element is added into the big O of 1. So the total time for resizing and adding the fifth event is big O of 4 plus big O of 1 equals to big O of 5. And then the cumulative time for the 8 events, so we break down for the 8 operation, the first 4 events, which is no resizing needed, each operation of big O of 1. So for events, so the time for event is 4 times with the big O of 1, which is big O of 4. And then for the fifth event, resizing needed, takes big O of 4, and then add the element takes big O of 1. So the time event is the big O of 5. And then for the next 3 event, which has no resizing needed, each operation takes big O of 1. So 3 events, 3 times with big O of 1, which is big O of 3. So the total for all this is big O of 4 plus big O of 5 plus big O of 3, which is big O of 12. And then for the efficiency of the algorithm is the amortized time complexity of adding an element is big O of 1, because the cost of resizing and distributed across all subsequent operations. So for the large numbers of addition, the algorithm remains efficient. I'll pass the conclusion to Umira.
Okay, thank you, Shazana, for the explanation. So for the conclusion is the event operation is efficient and well suited for managing events. Adding an event typically takes big O one time, as it involves creating an event object and appending it to the list. When the list is full, resizing occurs, which requires copying existing elements and takes big O n time. But this happens rarely. The total time complexity for adding an event is big O n, and the average time per event is big O one due to amortized efficiency. Display complexity is big O1, proportional to the number of the events stored. Overall, the algorithm is fast, scalable, and capable of handling a large number of events effectively. So, the conclusion is like the event operation design both efficient and scalable. So managing a large number of events, while adding an event usually takes constant time, like big O1. Occasional resizing of the list introduce a time cost of big O(n) due to copying elements. However, the resizing happens infrequently, so the average time complexity per event remains big O1 when considered over multiple operations. Thank you. So go to the next slide.
Okay, I will present for the last one, which is existing application code. So the first one that we choose is array list. It implements interface, which is list, which extends collection. Purpose is for stores dynamic list of objects. For example, events, attendees, or location that allow duplicates and maintain insertion order. So the operation is add E, adds an element to the list. Next, get integer index, retrieve an element by its index, remove the elements at the specified position. Size and clear, which is size is for returns the number of elements in the list. Clear, remove all elements from the list. So next is hash map. So the hash map is implement interface for map. The purpose is to store key value pairs. For example, mapping event IDs to event details. It does not allow duplicate keys, but allows duplicate values. So the operation that used in the hash map is put k key value. It's for adds or updates a key value pair. Next is for get object key. Retrieve the value associated with a key. Remove object key. Remove a key value pair by its key. Contains key. Checks if the map contains a specific keys. And the last one is key set, which is returns a set of all keys in the map. So next is hash set. It implements interface set, which also extend collection. The purpose is to store unique elements, ensuring there are no duplicates. For example, list of unique attendees names. It does not maintain insertion order. So the operation that exists on the hash set is add E, add S, and adds an element if it is not already present. Remove object, remove a specific element. Contains object, checks if a specific element exists. Size, return the number of unique elements in the set. And last one is clear, remove all elements from the set. So for the conclusion and summary, the LVL tree ensures the application maintains balanced and efficient data management. Operations such as insertion and deletion and search are optimized too. The application demonstrates how advanced data structures can solve real-world problems. And lastly is future improvements could include integrating additional features such as user roles and permission. So that's all for our presentation about the LVL. Thank you.